Hello everyone, my name is Muhammad Arif bin Tayabu, and today we are going to explore four major material classes, which is metals, polymers, ceramics, and composites, and compare their mechanical and sustainability characteristics. We will also look at how structure property relationships will influence durability, recyclability, and cost, and examine real examples where hybrid or composite materials outperform single material solutions. This presentation is aimed at multidisciplinary engineering audience, so I'll keep explanations intuitive and visual. Let's start with an overview of the four material classes. We have metals, polymers, ceramics, and composites. On the first hand, metals have a crystalline structure which makes them strong and ductile. Next, the polymers consist of long chain molecules. This means they are lightweight and flexible. Moving forward, the ceramics are built from ionic or covalent lattices, giving them hardness and brittleness. Last, we have composites combined by fibers and a matrix, giving it a tailored mechanical performance. This gives us the foundation to discuss the structure property relationships. Now, let's compare the sustainability factors of each material. On the first hand, we have the metals. Metals have high durability, high recyclability, and medium cost. Next, we have the polymers. The polymers have medium durability, low to medium recyclability, and low cost. Moving forward, the ceramics. The ceramics have very high durability but low recyclability and also cost high. Last but not least, the composites. The composites has high durability, low recyclability, and also high cost. Sustainability can't be assessed just by recyclability, durability, and cost, but the product's life cycle matters too. This slide illustrates the product cycle, also known as the product life cycle or life cycle assessment loop. It shows how a material or product moves through different stages from its creation to its end of life. Let me walk you through each part of the cycle. The first part is the raw material. The cycle begins with raw material extraction. This includes activities like mining metals, harvesting crops for biopolymers, or producing chemicals for plastics. This stage has significant environmental impact because it consumes energy and natural resources. Secondly, we have the production. Next, the raw materials are transported to a factory and undergo manufacturing or processing. Energy is required to melt, mold, shape, or assemble the product. At this stage, the choice of material strongly influences the carbon footprint and cost of production. Thirdly, the distribution. After manufacturing, the product is distributed to customers. This involves packaging and transportation by trucks, ships, or planes. The environmental impact here depends on distance, fuel use, and logistics efficiency. Following to the use phase. Once the customer receives the product, we enter the use phase. This may be a short or long depending on the material. Metals and ceramics typically enable long product lifetimes because they are durable. Polymers might degrade faster. Composites are long lasting but more complex to reuse. This stage determines how often a product needs replacement. Finally, the end of life. At the end of its useful life, the product can follow several possible routes. Recycling. Shown by the recycling symbol, materials like metals can easily re enter the cycle with minimal quality loss. Reincarnation or energy recovery. shown by the flame icon. Some polymers may be burnt for energy through this generates emissions. Finally, the disposal or the landfill, indicated by the question mark. When recycling is difficult, like for complex composites, the product often ends up in the waste. Here, we are going to connect the structure to sustainability. Fine grained metals have higher strength and longer life, which results to a reducing life cycle cost. Polymers rely on a chain orientation. It affects the mechanical performance and how easily they can be recycled. Ceramics have strong ionic bonds, making them durable but difficult to recycle. Composites rely on engineered interfaces to achieve high performance. But separating fibers from matrix materials make recycling difficult. Now, let's examine situations where composites outperform single materials. First of all, the CFRP in aerospace. Compared to aluminium or steel, carbon fiber composites are much lighter and have a higher strength to weight ratio. Secondly, the steel reinforced concrete. Concrete is strong in compression but weak in tension. Steel reinforcement solves this by providing tensile strength. Thirdly, metal ceramic cutting tools. Ceramics resist heat and wear, but metals add toughness. Combined, they create tools that maintain hardness at high temperatures. Number fourth, the fiber reinforced polymers in automotives. These reduce vehicle weight and improve energy absorption in crashes. Finally, the sandwich panels. Instead of using solid sheets, a lightweight core bonded between face sheets produces structures that are stiff yet light. So, why hybrids outperform single materials? Hybrids combine the strengths of multiple materials to overcome the weakness of each. This allows engineers to optimize for weight, strength, durability, and sometimes even cost, something no single material can achieve on its own. As a summary, the metals are strong, ductile, and recyclable. The polymers are lightweight and cheap, but may have limited durability. The ceramics are extremely hard, wear resistant, but brittle and hard to recycle. Composites provide tailored high performance but come with higher costs and recyclability challenges. Choosing the right material depends on balancing material needs, environmental impacts, and economic factors. Thank you for your time. I hope this presentation clarified how structure property relationships influence material behavior, sustainability, and why composite solutions are often the optimal choice in complex engineering applications.